In Chapter 4, we will be looking at cycloalkanes and stereochemistry of these cycloalkanes. And we have, again, our membrane channel, which allows chlorine to cross the cell membrane. And sometimes we have cyclic compounds that can cross these cell membranes. And cyclic compounds also occur often in pharmaceutical drugs. We have 1-aminocyclopropane carboxylic acid, which has this cyclopropane there with 3 carbons. This is used in the biosynthesis of ethylene. And then the globulol is a poisonous sesquiterpene that causes paralysis and delirium, and it comes from the rhododendron plant. So many organic compounds have rings of carbon atoms. So we have prostaglandin here. These are powerful locally acting vasodilators that inhibit the aggregation of blood platelets. So these prostaglandins are used to stop blood clots, and it's also used in vasodilation for inflammation. And we also have cortisone here, which has several cyclic structures, which you can see. This is a basic structure of a steroid. Cortisone is one of the main hormones that are released by the adrenal gland when we are stressed out, which you may be right now thinking about organic chemistry. Cycloalkanes are saturated cyclic hydrocarbons. They have the general formula of CnH2n, where n equals the number of carbons. So if we had a 4-membered carbon ring, it's going to have 2 times 4 or 8 hydrogens. So when we name our cycloalkanes, it's based on the carbon number, and we use those prefixes that we learned in the last chapter. We're just going to add cyclo to the front of the name. So instead of propane, because this has 3 carbons, this becomes cyclopropane. We have 4-membered ring, which is butane, so this becomes cyclobutane. We have cyclopentane. And then cyclohexane. To name the cycloalkanes, if it's not just the regular ring with no carbons on it, we're going to find the parent number, which we've already done we've shown in the last slide, and that's going to be based on the parent is based on the number of carbons in the ring. And then we're going to number substituents to give the lowest overall numbering. So here, this is numbered so that the methyl group gets 1, then it's 2, 3, 4, 5. And you can see the same structure drawn a couple of times, and the numbering here on this first structure will give us 2-ethyl if we go to name it. This will be 2-ethyl 1,4-dimethyl cycloheptane. So our substituents are at 1, 2, and 4, if you think about it that way. With the same structure, if I started numbering at the ethyl group, my numbers here would be 1-ethyl. My name would be 1-ethyl 2,6-dimethyl cycloheptane. So that overall numbering here is 1, 2, and 6. And then if for some reason I wanted to start my number 1 over here on the methyl group, the name here would be 3-ethyl 1,4-dimethyl cycloheptane. So the numbering here would be 1, 3, 4. So if the goal is to have the lowest overall numbering, the numbering system in the first example here, this is lower for the ethyl group, and the 1 is lower here. Our overall is 1, 2, 4, which is lower than 1, 2, 6, and then 1, 3, and 4. So we have the 1 and the 2, and the 4 is going to be lower than the 6 when we compare those two. So these are not the way that we want to name these structures. So if we have groups that are tied around the ring, where your numbering is tied, the group that comes first alphabetically gets listed first and gets the lowest numbering. In this particular situation, we have a 1,3-dimethyl cyclohexane. We're not going to have 1,5-dimethyl. And you don't just want to number around clockwise, we want to have the lowest overall numbering there. So 1,5 is going to be higher than 1,3. And in this situation here, the numbering would be tied either way. So we have a 1-ethyl 2-methyl or a 2-ethyl 1-methyl. In this case, we're going to use 1-ethyl 2-methyl because it's listed alphabetically. So if we can give the alphabetical one that's first, the first numbering, that is going to be preferred. And this one would otherwise be 2-ethyl 1-methyl. So we're going to stick with the first numbering on those two problems. If we have halogens present, we're going to treat them like alkyl groups. So if there's a bromine, it's going to be bromo, and then we have methyl. So the numbering here, actually we're going to give this the 1 because 1 comes first alphabetically. Bromo comes first alphabetically, and that will give us the lowest numbering. So this will be 1-bromo, 2-methyl cyclobutane. And in the next example, we have bromo at 1, and then now the numbering could be tied. So if I went clockwise, the methyl would be at 3, but ethyl would be at 5. And we're going to keep it so that if it's tied numbering, we're going to give it the lowest overall numbering and list it alphabetically. So this will be 1-bromo, 3-ethyl, 5-methyl, that's a 5, and cyclohexane. And if it's a chlorine, that's going to be chloro. Again, we're going for lowest overall numbering and alphabetical order. So this is 1-chloro, 3-ethyl, 2-methyl cyclopentane. And we've got some practice problems here. So we're going to name each of these. My parent here is 6 carbons, so this will be cyclohexane. And either way I number them, I'm going to have a 1,4. There's 2 methyl groups, so this will be 1,4-dimethyl cyclohexane. For this next problem, my parent is cyclopentane. I can number this way to give my methyl at 1 and then my ethyl at 3. If I number this way, my numbering is still 1 and 3, but I list ethyl first, so I'm going to use the green numbering. So this will be 1-ethyl 3-methyl. On C here, my parent is going to have 4 carbons. This will be cyclobutane. And when I have a group that's 3 carbons long, that's coming off of the ring, and it looks like a Y. This is my isopropyl. So 1-isopropyl cyclobutane. You can include the 1 if it's the only group, or you can leave it off. Either way is fine. When we have rings, these ones are not as flexible as open alkane chains, so we don't have as much conformational freedom in cycloalkanes. We can't just rotate it and change the conformation. So you can see our ethane there where it's being rotated around. This has shifted. And then we have cyclopropane. We can't rotate any of those bonds. Because of their cyclic structure, cycloalkanes are often viewed from the side, so we can see a top side and a bottom side. 1,2-dimethyl cyclopropane, there's 2 different isomers. And what you're looking at is where these wedges are, that point is coming towards you. And this is supposed to be a flat ring. It kind of looks like it's flat. And on this first one, we have the CH3 groups both coming off of the top side of that. So this is going to be cis 1,2-dimethyl cyclopropane. And on the second one here, one is coming off of the top side of the ring. This is coming off the bottom side. So this is trans 1,2-dimethyl cyclopropane. So cis just means that they're coming off of the same side, and then trans is the opposite side. So if you remember from the last couple chapters, we talked about constitutional isomers where the atoms are connected differently, but it has the same formula. So we have these 4 carbons here in the branched drawing, and then we also had butane, which was drawn in the straight chain. Those were 2 different isomers because they were connected differently. We can also have stereoisomers, which have the same connection but different 3D space. So the constitutional isomers are same formula, connected different. And stereoisomers have the same formula. They're connected the same, but in 3D space they differ. So in the case of the cyclopropane, we have 2 methyl groups that are pointing up or coming off of the top side. And then in the same cyclopropane, there's 2 methyl groups at 1 and 2, but this is top, this one's bottom, so this would be the trans, and this is the cis. Rings that are larger than 3 atoms will not be flat. These cyclic molecules can take on different shapes so that they can minimize their overlap. So if you think about the Newman projections, if they're flat, a lot of these things are going to overlap, and they don't want to do that. So bigger rings can have more conformations because they can kind of stretch out a little bit, and the smaller rings are more difficult to analyze and try to get into a comfortable position. So cyclopropane, these sp3 carbons want to be 109.5 degrees, but they can't be tetrahedral. In cyclopropane, at most they can be 60 degrees. So that's kind of a long way from them being in a flexible position where they can rotate and move around. There's going to be a lot of angle strain here. And with cyclobutane, it's grown a little bit to 90 degrees, but we still have angle strain. Cyclopentane is much closer. And in cyclohexane, we have these greater than tetrahedral bond angles. So cyclopropane is the most strained of all of the rings because it has those 60-degree bond angles. If we looked at a Newman projection, everything is going to be eclipsed there. In cyclobutane, we have torsional strain, which has some of that, which has some bond angle strain, and things are not quite eclipsed, but they're also not staggered. In cyclopentane, there's no angle strain, just torsional strain. So this can twist and pucker up to form an envelope shape. Kind of hard to see there, but the Newman projection shows that it's not eclipsed, but it's not exactly staggered, so it kind of puckers to get into a position where it can get away from each other as far as possible. The cyclohexanes can adopt what's called chair shape, and these occur widely in nature, these cyclohexanes. It's free of the angle strain and torsional strain. The conformation has alternating atoms or carbons in the common plane, and all of these carbons can have tetrahedrals. So menthol is a naturally occurring compound that you may have heard of. That one has a cyclohexane with different groups coming off of there. The wedges and the dashes are going to indicate what direction those groups are pointing. So when these cyclohexanes form this conformation where it can be tetrahedral between all the carbons, this is called a chair conformation. So it kind of looks like a chaise lounge, like one of these beach chairs that you might see in the summertime, and it's drawn kind of like this chair. If we look at the Newman projection down the 1, 2, and the 5, 4 bond, we can see it. This is anti-staggered, which is why we don't have any of that angle or torsional strain. The key to drawing the cyclohexane chairs is to draw 3 sets of parallel lines. If I start with the first set here, there's one set. The next one you're going to take off of one of the corners and draw those 2 parallel to each other, and then you can just connect these. And that's going to make your chair. The groups that come off of this chair, so if I drew another one, are going to be parallel to the groups that you just drew. So if I have an up group there and a down group here, that's parallel to the blue lines. This is going to be down, this will be up, and that's parallel to the red lines. And then I have an up and a down here. And those are all parallel to each other. Cyclohexane is going to have 6 axial hydrogens, which are perpendicular to the ring. Those will stick straight up and down. So axial, you can think of axis. These go straight up and down. And then we have 6 equatorial hydrogens. And those come out kind of like at the equator, so they go out at an angle. So up, down. The angle is parallel to the bonds of the ring. And equatorial, you can think of equator. So the ring axis is going straight up and down. So all of these red bonds here, these red things sticking up, these are all axial hydrogens. And then there's the ring equator. Those were the parallel lines that came out at an angle that we drew in the last slide. And those are coming out at an angle to the side. So we have, these are all the equatorial ones. So each carbon has a group that's up and one that's down. And each carbon has one equatorial, one axial. And those rotate around each of the carbons. So on this first carbon here, there's an axial up and equatorial that's pointing down. That hydrogen goes out to an angle down to the side. On the next carbon here, this one has one equatorial up and the other one is axial down. So that rotates every other carbon. So this one's axial up. This one is equatorial down. This one is equatorial up, axial down. The next one is axial up, equatorial down, and it keeps rotating back and forth on every carbon. Chair conformations can flip back and forth to each other, which results in the exchange of axial and equatorial positions. And that's done by a ring flip. And what that is saying is that all the groups that were axial become equatorial. And the group direction stays the same. So all of these red atoms in the first structure are axial up on top. These are axial down on the bottom half. And then once we do the ring flip, all of the red that were axial up or down become equatorial up. And then the other ones became equatorial down. So if it was axial up before, it became equatorial up. So if this one right here is the same as this one. So all of the axial ups became equatorial up. The direction stayed the same. They're still up, but it just went from axial to equatorial. And all the axial downs are still down, but now they're equatorial. And by that same thing, the blue were all equatorial. And when we did the ring flip, they became axial. If they were up in the first ring structure, they stay up in the second, but they've just switched from equatorial to axial. So you can kind of see the ring flip when we draw it. When we're doing the ring flip, you can think of this dotted line that we're drawing here. The gray carbon that's circled gets flipped down, and then we flip the green carbon up. And that gives us the ring flip. And again, all of our axial substituents become equatorial, and all the equatorials become axial. We want to draw chair conformations of bromocyclohexane, showing all of the hydrogen atoms and labeling positions as axial and equatorial, and then figuring out which one is more stable. We're going to draw in the axial groups first, and I'm going to do those in red. The bromine on the first one, because it's pointing straight up and down, that's axial. If this one is axial up, the next one here is going to be axial down, and I can decide what is axial by looking at the corner. This corner is pointing down, so whatever's in the down direction is going to be axial down. On the next carbon over, this is a corner that's pointing up, so my axial group is up. This is pointing down, so my axial group is down. This is up, so this is axial up. This is going to be axial down. So every other carbon is going to be axial up, and then the in-between ones are going to be axial down. And each carbon we said has an axial, so the other group on this carbon is going to be equatorial, and the direction is down here, and it'll be down and at an angle. So this one is parallel to this carbon group right here. This carbon already has a hydrogen that's axial, so my other substituent is going to be equatorial. This is equatorial down, and this one is parallel to this set of lines here. This one is parallel to this set of lines right here. This is equatorial up, equatorial down, and this one's equatorial up. So all of my hydrogens are parallel to a set of the carbon bond lines. And so all of the blue here are going to be equatorial, and the red are axial. When we do the chair flip, all of my axial groups now become equatorial. So bromine is still up, but now it's equatorial. So all of my hydrogens that were there are now going to be equatorial. And I can use the same rules where the corner is going to tell me what is axial up or down. So this corner is pointing down, so my down group is axial, and this is pointing up, so my axial group is up. This is down, so this is down. And I have axial up, this is axial down, and this corner is pointing up, so my up group is going to be axial. And to determine which one is more stable, the conformation where the large group is in the equatorial position is most stable. So being stable in the equatorial position is preferred.